Hello dear students, in this video I'll continue with the one-shot revision series for the CBSE board exam. The next chapter which we have is chapter 3C, which is on differential equations and modeling. So the major topics in differential equations consists of, the first one is finding the order and degree. Then we have solution of a differential equation. It consists of general solution and particular solution. And next topic is formation of a differential equation. The last topic is mathematical modeling using differential equations. Under this mathematical modeling, we have the growth model and the decay model. First, we will see what are differential equations. If we have a function of the form y equal to f of x, when we differentiate this function y with respect to x, if we get a function say g of x, then we say this dy by dx equal to g of x is a differential equation, where this g of x is nothing but it is the derivative of f of x. So an equation involving derivatives of the dependent variable with respect to the independent variable, it is called a differential equation. So it can be an equation involving derivative or derivatives of the dependent variable with respect to independent variables. So here we have only one dependent variable y and one independent variable x. Next we have order of a differential equation. The order of differential equation, it is defined as the highest order derivative of the dependent variable with respect to the independent variable which is involved in the differential equation. Say for example, if the differential equation has say d square y by dx square, then the order of differential equation is 2. That is the highest order derivative that is present in the differential equation. Say if the highest order derivative present in the differential equation is d4y upon dx4, in this case the order is 4. And next we have degree of a differential equation. For degree of differential equation to be defined, it must be a polynomial equation in its derivatives. So only when the differential equation is a polynomial equation in its derivatives, that is, it should be of the form dy by dx plus d square y by dx square, it can be even the whole square plus some constancy equal to 0. So here only when the differential equation is a polynomial equation in its derivatives, then the degree is defined. On the other hand, if we have a differential equation of the form e raised to dy by dx plus d square y by dx square equal to 0, here in this case the degree of the differential equation is not defined, because here the differential equation, it is not a polynomial equation in its derivatives. So to find the degree of a differential equation, it should be defined. The degree of a differential equation when it is a polynomial equation in its derivatives is the highest power of the highest order derivative involved in the differential equation. So the degree of this differential equation is, it is the highest power of the highest order derivative. Here the highest order derivative is d square y by dx square, and this is raised to 2. So here in this case the degree of differential equation is 2 in this case. So this is with respect to order and degree of a differential equation. And now we will see the first example. Find the order and degree if defined of the following differential equations. So the first one is dy by dx equal to ky, where k is a scalar. So here the highest order derivative is dy by dx, and it is a first order derivative, so the order is 1 and it is raised to the power 1. So degree is also 1, and it is a polynomial equation in derivatives. The next is ds by dt the whole raised to 4 plus 2s into d square s by dt square equal to 0. So here the highest order derivative is d square s by dt square. So the highest order is second order. Order is 2. And this is raised to 1. So degree is 1. And next we have the third subdivision. 1 plus dy by dx the whole cube equal to d square y by dx square the whole square. So here the highest order derivative in this differential equation is a derivative of this second order. So here the order is 2 and this is raised to 2. So the degree is also 2. And next we have y dx plus x log y by x dy minus 2x dy equal to 0. So here this is a differential equation, but it is not written in the polynomial form. So let us write it in the polynomial form. So here if we take minus dy outside, we will have 2x minus x log y by x equal to this, we can transpose to the other side. It will be minus y dx. So minus minus will get cancelled. Dy by dx will be y by 2x minus x log y by x. So this is a differential equation which involves dy by dx is equal to some function of x and y. So here it is a first order derivative dy by dx, so the order is 1 and it is raised to the power 1. So degree is also 1. So this is how we have to go about in finding the order and degree of the differential equation. Sometimes in the question paper they may ask find the product of order and degree of the differential equation. In that case we have to multiply the order and degree and give the answer. Let us move on to the next topic, which is general and particular solution of a differential equation. So when we have a differential equation of the form dy by dx equal to some function of x, then in this case we have to solve the differential equation and we have to find y in terms of x, or it can be a function of the form f of x, y and arbitrary constants c1 and c2. So such a solution is called a general solution of the differential equation. So the function involving the variables and independent arbitrary constants is called the general solution of the differential equation. So here if we have a general solution of differential equation in two variables x and y and two arbitrary constants c1 and c2, then the general solution takes the form a function of x, y, c1, c2 equal to 0. And next we have the particular solution. When these arbitrary constants c1 and c2 have certain values, then such a solution is called a particular solution. So here a solution obtained from the general solution by giving particular values to the arbitrary constants is called a particular solution of the differential equation. So a particular solution in two variables x and y does not contain any arbitrary constant and it is of the form f of x, y equal to 0. So this is with respect to general solution and particular solution. Now we will see some examples. Verify that the function y is equal to a e raised to bx is a solution of the differential equation d square y by dx square minus b square y equal to 0. So here we have to verify that this function y equal to a e raised to bx, it is a solution of this differential equation. So here given y equal to a e raised to bx. So we have to verify using this differential equation and it has got d square y by dx square. So we have to differentiate this twice. dy by dx is ab e raised to bx and d square y by dx square. It is a b square e raised to bx. So this is nothing but b square into a e raised to bx. A e raised to bx is y. So this is b square into y. So from this we get d square y by dx square minus b square y equal to 0. Hence y equal to a e raised to bx is a solution of the given differential equation. So this is how we have to verify whether a given function is a solution of the differential equations. Next question, verify that y equal to c into e raised to minus x cube is the solution of the differential equation dy by dx plus 3x square y equal to 0. Also determine the solution curve of the differential equation that passes through the point 0, 5. So here the differential equation consists of only dy by dx. So we can differentiate once and verify whether this function is a solution of this differential equation. And to find the solution curve which passes through this point, we can put x as 0, y as phi in the solution curve, find c, and then we can find the solution, the particular solution of this differential equation. So here given y equal to c e raised to minus x cube. So let us differentiate this with respect to x. dy by dx is equal to c into e raised to minus x cube. We have to use chain rule to differentiate this. So e raised to x is e raised to x only. So e raised to minus x cube will be e raised to minus x cube. Then the derivative of minus x cube. So minus 3x square. So this is equal to minus 3x square into c e raised to minus x cube. So this c e raised to minus x cube is nothing but it is y. So this is equal to minus 3x square y. So let us substitute dy by dx and y in this differential equation. So the left hand side is dy by dx plus 3x square y. This is equal to dy by dx, we got it as minus 3x square y minus 3x square y plus 3x square y. This is 0, which is the right hand side. Therefore, the given function is a solution. And next we have to determine the solution curve that passes through 0, 5. At 0, 5, one implies 5 is equal to c into e raised to 0, implies c equal to 5. Therefore, the required solution is y equal to 5 into e raised to minus x cube. So this is the solution curve which passes through the point 0, 5. Next question, verify that y equal to 1 by x minus log x is a solution of the differential equation x square d square y by dx square plus x dy by dx minus y equal to log x. So here we have the solution. We have y equal to 1 by x minus log x. So in this differential equation we have dy by dx and d square y by dx square. So we have to find up to the second order derivative. So first let us differentiate with respect to x. Dy by dx equal to minus 1 by x square minus 1 by x. And next we have d square y by dx square. So this is equal to, this is nothing but minus x raised to minus 2 minus x raised to minus 1. So derivative of x raised to minus 2 is, it is minus 2 into x raised to minus 2 minus 1. So it is minus of minus 2 into x raised to minus 3 minus minus 1 into x raised to minus 1 minus 2. So this is 2 by x cube plus 1 by x square. Now let us consider the left hand side of this given differential equation. The left hand side is x square d square y by dx square plus x dy by dx minus y. This is equal to x square into, here we have d square y by dx square. 2 by x cube plus 1 by x square plus x into dy by dx is minus 1 by x square minus 1 by x cube. minus 1 by x minus y is 1 by x minus log x. So it is minus 1 by x plus log x. Now let us simplify this. So this is 2 by x plus 1, and here x into minus 1 by x square is minus 1 by x, then minus 1, then minus 1 by x plus log x. So here plus 1 minus 1 will get cancelled. Here we have 2 by x minus 1 by x minus 1 by x. So it is 0. We are left with log x. This is equal to the right hand side. So we have log x in the right hand side. So we got left hand side equal to the right hand side. Therefore, the given function is the solution. Next we have the next question. Show that y square equal to 4ax is a solution of the differential equation y equal to x dy by dx plus a dx by dy. So here first let us write the given function. We have y square equal to 4ax. Now let us differentiate this with respect to x. We have 2y dy by dx equal to 4a. So from this we get dy by dx equal to 4a by 2y, or it is 2a upon y. So here in the differential equation we have dx by dy. So if we differentiate the given solution with respect to y, we will get y by 2a. Now let us consider the right hand side of the differential equation. X dy by dx plus a dx by dy. It is equal to x dy by dx is 2ax by y plus a dx by dy will be a into y by 2a, or it is y by 2. A into y by 2a, which is y by 2. So here the LCM is 2y. Here we have 4ax plus y square. Now 4ax is nothing but it is y square. So y square plus y square is 2y square. 2y square upon 2y. This is equal to y, which is the left hand side. So we got the right hand side equal to the left hand side. Therefore, y square equal to 4ax is a solution of this differential equation. Therefore, the given function is a solution of the given differential equation. The next topic is formation of a differential equation. So here we have the steps to form a differential equation. Now let us assume that the given family of curves f, it depends on the parameters a and b. Then we can represent it in the equation form as f of x, y, a, b equal to 0. If we differentiate this equation with respect to x, then we will get a function of the form g of x, y, y prime, a, b equal to 0. So even after doing this, from 1 and 2 we may not be able to eliminate the parameters a and b. So we have to obtain a third equation, which is obtained by differentiating this equation 2 with respect to x, so that we get a function of the form h of x, y, y prime, y double prime, a, b equal to 0. So the required differential equation, it can be obtained by eliminating a and b from 1, 2 and 3. As a result, we get the differential equation as f of x, y, y prime, y double prime is equal to 0. So if the given family of curves, if it has got n parameters, then it has to be differentiated n times to eliminate the parameters and obtain the nth order differential equation. So we usually have only 2 parameters, so it is enough if we obtain up to the second order differential equation. Now we'll continue with the examples. Form a differential equation representing the family of parabolas having vertex at the origin and axis along the positive direction of the x-axis. So here we have studied about parabolas in class 11. So here this is the family of parabolas having vertex at the origin and axis along the positive direction of the x-axis. So it is given by equation of such parabolas is x square equal to 4ay. Now here we can see that we have one parameter, so it is enough if we are able to eliminate this parameter from this equation and the first order derivative. So let us take this as 1. Now let us differentiate 1 with respect to x. So that we get 2x equal to 4a dy by dx. From this we get dy by dx equal to 2x by 4a, or it is x by 2a. So here from 1 we have a as x square by 4y. This implies a equal to x square by 4y. So that a we can substitute here. Dy by dx is equal to x by 2 into x square by 4y. So this is 2y by x, which implies x dy by dx equal to 2y. So this is the required differential equation which represents the family of parabolas having vertex at the origin and axis along the positive direction of the x-axis. Next we have the next question. Form a differential equation representing the family of curves having given by y equal to a e raised to bx. So here we can see that this function has got two parameters a and b. They are the arbitrary constants. So we have to proceed up to finding the second order derivative. We have y equal to a into e raised to bx. Let us differentiate 1 with respect to x. So we get dy by dx equal to ab into e raised to bx. So in place of a e raised to bx we can put y. So this is equal to by. Now let us find the second order derivative. D square y by dx square equal to b into dy by dx. So here in place of b we can put 1 by y dy by dx. This implies b equal to 1 by y dy by dx. Let us take this as 2. So 2 implies d square y by dx square equal to, or from 2. From 2, d square y by dx square equal to 1 by y dy by dx. There is already 1 dy by dx. So this implies y d square y by dx square equal to dy by dx the whole square. So this is the required differential equation which represents the family of curves given by y equal to a e raised to bx. Next we have the next question. Form the differential equation of the family of hyperbolas having foci on x-axis and center at the origin. So here we have to form the differential equation of the family of these hyperbolas having the focus on the x-axis and center is at the origin. So the required equation of such parabolas, it is given hyperbola as it is given by of the family of hyperbolas it is x square by a square plus y square by b square equal to 1. Let us take this as the first equation. Let us differentiate this with respect to x. So we get 2x by a square plus 2y by b square dy by dx equal to 0. Or from this we get y by b square dy by dx equal to minus x by a square. So here if we are able to write this as the variables on one side and constant on the other side, then we can, if we differentiate again, we will be able to get rid of the constants. So this dy by dx, let us write it as y1. So y by x into y1 equal to minus b square by a square, where y1 is nothing but dy by dx. Again differentiating with respect to x. So here let us differentiate this again. So d square y by dx, let us write it as y2. So we have to use the quotient rule to differentiate this. Denominator is x, so it is x square. Then x into, we have to differentiate the numerator. y1 into y1 plus y into y2. That is the second derivative of y1 minus y1. This is equal to 0. So from this we get x into y1 square plus y2 minus y1 equal to 0. So this is the required differential equation of the family of hyperbolas having foci on the x-axis and center at the origin. Next topic is we have solving a simple differential equation. So if the given differential equation is of the form dy by dx is equal to f of x. So in this case we can write this as dy equal to f of x dx. Now this we can integrate. So integral dy will be integral f of x dx, or we have y is equal to integral f of x dx plus some constant c. And next we have the next case where we have dy by dx equal to some function of y. So in this case we can write this differential equation of the form dy by g of y equal to dx. Then we can integrate this on both sides so that we get x is equal to integral dy by g of y plus c. Next we have the next case where the differential equation is of the form dy by dx is equal to a function of x and y. So in this case if we are able to write the given differential equation as a function of x into some other function of y, then in this case we can write dy by g of y equal to f of x dx. Now we can integrate both sides. Equal to integral f of x dx plus c. So this is how we can proceed for different types of differential equations to find the solution. Let us continue with the examples. Find the general solution of the differential equation dy by dx plus y equal to 1. So here this is of the form dy by dx equal to f of y. So here this we can write it as dy by dx equal to minus of y minus 1, or dy by y minus 1 equal to minus dx. Let us integrate both sides. Dy by y minus 1 equal to minus integral dx, or log mod y minus 1 equal to minus x plus c. This is log mod y minus 1 to the base e. So from this we get y minus 1 equal to e raised to minus x plus c, or it is e raised to minus x into e raised to c. This e raised to c we can write it as some other constant k. So y minus 1 equal to k e raised to minus x, or y is 1 plus k e raised to minus x. So this is the general solution of this given differential equation. Next question, solve the differential equation y log y dx minus x dy. It is equal to 0. So first let us collect all the x terms and on one side and y terms on the other side. So y log y dx minus x dy equal to 0 implies y log y dx equal to x dy. So from this we get dx by x equal to dy by y log y. Now for integrating we can use any of the methods of integration that we have learnt to find the integral of these. So if we integrate both sides, integral dx by x equal to integral dy by y log y. So for this we have to use integration by substitution. So let us put t equal to log y. So dt will be dy by y. So from this we get integral dx by x equal to integral dt by t. So here if we integrate, we get log x plus log c, log mod x plus log c equal to log mod t. Now log a plus log b is nothing but it is log ab equal to t we have taken as log y, log of log y. So from this we get xc is equal to log y, or log y equal to x into c. This is to the base e. So from this we get y is equal to e raised to cx. This is the solution of this given differential equation. Next question, dy by dx is equal to e raised to x plus y plus x square into e raised to y. So let us rewrite this differential equation as e raised to x plus y is e raised to x into e raised to y plus x square e raised to y. So this is e raised to y is common, we can take it outside, into e raised to x plus x square. So we have dy by e raised to y equal to e raised to x plus x square dx. So from this we get e raised to minus y dy equal to e raised to x plus x square dx. Let us integrate both sides with respect to, let us integrate both sides. So integral e raised to minus y dy will be minus e raised to minus y equal to integral e raised to x is e raised to x, integral x square dx is x cube by 3 plus c. So from this we get e raised to x plus e raised to minus y plus x cube by 3. If we take this as some constant c1 equal to c. So this is the required solution of this given differential equation. Next we have the next question. Find the particular solution of the differential equation dy by dx is equal to x into 2 log x plus 1, given that y equal to 0 when x is equal to 2. So they have given, we have to find the particular solution for this differential equation. Since they have given at y equal to 0, x is equal to 2, we can substitute that and find the constant. So this we can write it as dy is equal to 2x log x plus x into dx. Now let us integrate both sides. So we get integral dy is equal to 2 into integral x log x dx plus integral x dx. So this integral we know. Let us integrate x log x dx using integration by parts. Consider integral x log x dx. So here we have to take log x as the first function and x as the second function. So it is log x into integral x dx minus integral derivative of log x into integral x dx plus c1. So this is x square by 2 log x minus integral 1 by x into x square by 2 dx plus c1. So here we have integral x dx, which is x square by 2. There is already 1 by 2. So it is x square by 4 plus c1. So 1 implies integral dy is y equal to 2 into, for integral x log x dx, we got this. Let us take this as 2 x square by 2 log x minus x square by 4 plus c1 plus integral x dx is x square by 2 plus c2. This is from 2. So from this we get y is equal to x square log x minus x square by 2 plus x square by 2. So here plus 2 c1 plus c2, let us have it as a single constant c. So minus x square by 2 plus x square by 2 will go. So we get y as x square log x plus c. Here they have given y equal to 0 when x is equal to 2. Y equal to 0 when x equal to 2 implies 0 equal to 4 log 2 plus c, or c equal to minus 4 log 2. Therefore, the solution is y equal to x square log x minus 4 log 2. So this is the required particular solution for this differential equation. The last topic in differential equations is differential equations and mathematical modeling. So how we can formulate a mathematical model of a physical problem. First we have to identify the physical problem, and then we have to formulate the physical problem in terms of a mathematical model. The next step is we convert this into a differential equation. Then we find the solution of this differential equation. After finding the solution of the problem, we will interpret the solution. So this is how differential equations are useful in mathematical modeling. So under mathematical modeling, we have various growth and decay models. The mathematical model for exponential growth or decay, it is given by f of t equal to a into e raised to kt, or it can be written as y equal to a into e raised to kt. Here t represents the time, a represents the original amount, and y or f of t, it represents the quantity at any time t, and k, it is a constant which depends on the rate of growth or the rate of decay. If the k we have here, if this k is more than 0, then this formula will represent exponential growth. On the other hand, if this k, if it is less than 0, then this formula or this solution, it represents exponential decay. So this is the case when there is exponential growth in the quantity. Here we have y equal to a into e raised to kt, and this is the case where we have exponential decay in the quantity, and it is given by y equal to a into e raised to minus kt. Here k is less than 0. And this the first model is the population growth model. Suppose that P of t is the number of individuals in a population. It can be of humans or insects or bacteria having a constant birth rate alpha and a constant death rate beta. Then the rate of change of population P of t with respect to time, it is given by dP of t upon dt. This is equal to alpha minus beta into P. Now this alpha minus beta is considered as the constant of proportionality given by K. So from this we get dP by dt equal to K into P. Here we can see that this is of the form dP by dt as a function of P. So we know how to solve this differential equation. From this we get dP by P equal to K dt. We can integrate both sides. DP by P equal to K integral dt, or we get log P equal to Kt plus the constant C. This is log P to the base E. So from this we get P equal to e raised to Kt plus C, or P equal to e raised to Kt into e raised to C. This e raised to C we can have it as some lambda. So P equal to e raised to Kt into lambda. So this is the population growth model. Next we have the next model given by, which is used to find the compound interest. Say a person deposits an amount A of t at a time t in years in a bank, and suppose that the interest is compounded continuously at an annual interest rate R. To obtain the differential equation which governs the variation in A with respect to time t, we follow the following steps. So during a short time interval delta t, the amount of interest added to the account, it is approximately given by delta A equal to R into the original amount A of t at time t into delta t. So from this we get delta A upon delta t equal to R into A of t. Now if here we are considering that interest is compounded continuously. So if we take limit t tends to 0, delta A by delta t equal to R into A, or we have dA by dt equal to R into A. So from this we have dA by A equal to R into dt. Now we can integrate both sides. dA by A equal to R integral dt. We get log A equal to RT plus C. So this is log A to the base E. So from this we get A equal to e raised to RT into e raised to C. If at time t equal to 0, if the original amount deposited was A naught, then we have, here we can put A as A naught and T as 0. A naught equal to e raised to 0 into e raised to C. So for e raised to C we can put A naught. Therefore A equal to A naught into e raised to RT. So this is the model which can be used for compound interest. Next we have Newton's law of cooling. So according to Newton's law of cooling, the rate of change of temperature T of a body it is proportional to the difference between T and the temperature of the surrounding medium A. So we have dt upon dt. It is equal to some constant of proportionality K with a negative sign, because if we have a hot body which is taken in a medium whose temperature is low, then the temperature of the hot body will start decreasing. As a result, we have a negative sign here. So it is minus K into T minus A. So from this we get dt by T minus A equal to minus K dt. This we can integrate on both sides. So from this we get log T minus A equal to minus Kt plus C. This is to the base E. So from this we get T minus A equal to e raised to minus Kt into e raised to C. So for this e raised to C we can put lambda. So we have T minus A equal to lambda into e raised to minus Kt. So this is the model for Newton's law of cooling. Next we have what is known as carbon dating. Carbon 14, also known as radiocarbon, it is a radioactive form of carbon that is found in living plants and animals. Now this radiocarbon, it disintegrates after the plant or animal dies. Now if we want to estimate the remains of plants or animals that the scientists or archaeologists are finding, the age can be estimated by comparing the amount of radiocarbon in the remains of plants or animals with those living plants or animals. This technique, it is called carbon dating. So if we consider let A of T be the mass of carbon 14 after T years, then we have dA by dt. It is proportional to A. Now here we can see that the mass, it disintegrates or it decays. So it is a decay model. As a result, we have the constant of proportionality as negative. So it is dA by dt equal to minus K into A. So from this we get dA by A equal to minus K dt. This we can integrate on both sides. We get log mod A equal to minus Kt plus C. This is to the base E. As a result, we get A equal to e raised to minus Kt into e raised to C. If we consider at T equal to 0, A equal to A naught. That is, if we find the mass of carbon 14 in the living plants or animals as A naught. So we have at T equal to 0, A equal to A naught, which implies A naught equal to e raised to 0 into e raised to C. So we get e raised to C as A naught. Therefore, A equal to A naught into e raised to minus Kt, where A naught is the mass of carbon 14 in living plants or animals, which is being compared with the remains of plants of animals. Next we have the last model, which is drug assimilation into the blood. Say if we take the case of a single common cold pill which is consumed. So when the pill is taken, it first dissolves into the gastrointestinal tract and each ingredient is diffused into the blood. Then these are carried to different parts of the body on which they act, and they are removed from the bloodstream by kidneys and liver with different rates. So when the drug is taken, it goes into the gastrointestinal tract, diffuses into the blood, and it is taken to other parts of the body where it has to react, and finally it leaves the bloodstream by kidneys and liver. So if we want to find the amount of drug at any time t that is present in the body, then if we consider let x of t be the amount of drug at time t in the gastrointestinal tract, and let x of 0 or x naught is the amount of drug which is taken initially, then we have dx of t upon dt. This is proportional to the amount of drug x, or we have dx by dt equal to minus k into x. Here again, this is a decay model. That is the reason why we have a negative sign here, because over a period of time, the amount of drug reduces in the bloodstream. So from here we have dx by x equal to minus k dt. This, when we integrate on both sides, we get log mod x equal to minus kt plus c. This is to the base e. As a result, we have x as e raised to minus kt into e raised to c. Now we have taken at time t equal to 0, x is x naught. So as a result, we will get e raised to c as x naught. So this implies x is equal to x naught into e raised to minus kt. So this is the mathematical model for drug assimilation into blood. So the various example questions for each of these mathematical model, I have already made a video. The link is available in the description. So these are the various topics in differential equations. I hope this video was useful for you. If you have not subscribed to my channel, please subscribe. If you find this video useful, share it with your friends. Thank you for watching.